All right. So the only thing different about this lesson is just the concept of a tangent line, and a tangent line is just any line that hits the curve at exactly one point. All right. And today it's just the gradient of a point on a curve is going to be the same as the gradient of that tangent line. So lines have constant gradients, but curves don't. So if we pick a point anywhere on the curve and we say, what is the gradient? The gradient of the curve at that point is the same as the gradient of the line. So we're gonna, use this terminology. These are the same thing. All right, that's kind of why I wrote this here. Just very, gradient at point on curve equals gradient of the tangent. Should say line. Okay, so in this example, we're going to find the gradient of the tangent of this curve at this point. So what we're going to do is differentiate this and substitute 4 for x, just like we did in the last lesson. The only thing different is the words up here. So when we differentiate it, dy by dx, and if you want to just do y dash to show you're differentiating that, that's fine. I think we all were able to do this. This is 3x squared plus 2, and that differentiates to 0. And when x equals 4, I substitute 4 for x. And this would be done on the calculator, or not. 16, 4 squared is 16, 16 times 3. And 48 plus 2 equals 50. Pretty steep gradient. Okay, so let's look at another example where instead of giving the x value, I just give the coordinate, like this. Okay, so suppose I have the original function here. It would be a parabola, some curve, y equals x squared minus 8x plus 1, at this point. Nothing different in that. I differentiate it. And when I differentiate it, I did a different notation here. If you don't like dy by dx, you can write just y dash, same thing. There's the gradient function. Now, here I just had an x value and I substituted it in here. Where here I'm given x and y. Well, the easy thing you need to remember is you don't care about y on that point right there. The only thing you need to substitute in is the x value, which coincidentally it's the same number. So if you're given a point, all you need to do is plug in that x value there. And for this equation, it looks like the gradient at this point would be 0, which means that would be the turning point, okay, or a stationary point. So this would be a smiley face parabola. I don't know what exactly the shape is, but 4, negative 15 would be right here. And the gradient of that tangent line would be 0. So these next examples, what we're going to do is I'll give you the gradient, and you're going to have to find the point on that curve where it is that gradient. Okay? So let's look at the first example. Okay, so here's my original function, and what point on this curve, which would be a parabola, what point on this curve would the gradient be negative 3? Okay? So what I'm going to do is, first thing, like always, is differentiate it. Not like always, but in this lesson, I guess. 4 times 2 is 8. 2 minus 1 is 1, so that's 8x. And this is minus 7. Okay, so that's the gradient function. And the gradient is negative 3. So what that means is I'm going to substitute f dash x for negative 3 because I'm given the gradient. So I substitute that in there and solve for x. And I've got a simple linear equation here to solve for x. Nothing too major here at all. You can do it on the graphics. Add 7 to this side. And then I'll divide by 8. And it looks like I'll get 4 divided by 8 gives me a half. So I use a decimal because it's non-terminating. It's terminating and it doesn't recur. Okay, so I'm not finished. So what I've done is I've solved for the x-coordinate, but how do I find the y-coordinate? I've got half of it. I want the point. So to get this, what I'm going to do is take this x value and substitute it back into the original equation to find the y-coordinate. Okay, so here's the x. The second part is to substitute it back into the original here. So when I substitute that 0.5 in for x in here, I can do the rest on the calculator to find the y-coordinate. Okay, so when I substitute that back into the original equation, coincidentally, I do get 0.5, which is the y-coordinate. So the point is, x is 0.5, and y is 0.5. They won't always be the same. Okay, so we differentiate, solve for x, take that x and plug it back into the original equation to find the y-coordinate. This is x, and this is y. And remember, f of x is the same as y for this example. Those are the same thing. Those are interchangeable. Okay, let's look at one more example where the gradient function isn't a linear equation. That's kind of easy to solve. Any of these are easy to solve if we use the graphics calculator, but let's look at another one. All right, so the difference with this example is, what's the difference? Points. There's going to be more than one point on this curve where the gradient is negative 14. And possibly the reason is because this one's a cubic and not a parabola. So this is x cubed, so this will do something like up, down, up. Won't be exactly that shape, but it will have 2 points on the curve where it's this gradient. Okay, so similar to last one, we're going to differentiate this and set that equation equal to negative 14. So we do f dash x, which is a gradient function. X cubed differentiates to 3x squared. This differentiates to 18x. This differentiates to plus 10. And that differentiates to 0. Next up, this is equal to negative 14. Rewrite this equation. 3x squared minus 18x plus 10. Now, right now, I've got a quadratic, which even if you do it on the graphics, it needs to be set to 0. So all quadratics, whether you're doing it factorizing, which I'll do it without a graphics, or on the calculator, they need to be set to 0. So what that means is I'm going to add 14 over here to get 3x squared minus 18x. When I add the 14 to here, I get positive 24. Now from here, you can solve it on the graphics, or you can factorize it. I'll factorize it because it's more fun. First thing I notice is that there's a common factor of 3 within all the terms, so I factorize that out. Now I factorize this polynomial in here. What factors of 8 add up to negative 6, and that's x minus 2 and x minus 4. So that means my two solutions, I should get two values of x because there's 2 points, are x equals 2 or x equals 4. So those are the two x coordinates for my 2 points. So now you might be able to see what you're going to do. Substitute x equals 2 into the original equation to find the y-coordinate. Get it? That's 1 point. And then substitute x equals 4 into the original equation as well to find that y-coordinate. You get 2 different points. So I'll do this one first, x equals 2, and plug it in here, which would be done on the calculator. That's what it looks like. That's what it would look like on your calculator when you substitute it back into the original equation. Okay, so when x equals 2, y equals negative 13. That is my first point. 2, negative 13. The gradient is negative 14. So now we plug in x equals 4 into the original equation, and that'll give you the other y-coordinate.
Do we need to find both?
Yeah, both. Find the coordinates of the points, I guess, plural. That's what it looks like when I substitute it in. And I should get negative 45 here. Okay, so that's my second point. When x equals 4, y will give me negative 45. And don't forget, f of x is the same thing as y. So I've got my two coordinates right here, which are going to have that gradient of negative 14 on that cubic, on that graph that's going to be roughly that shape.